So thank you for your nice introduction. Thank you also for you all for being here for my PhD defense. Today I'm going to present the outcome of a PhD project focusing on microsite sources, which is one of the most omnipresent and persistent and type of the microseismic sources that we have. And we would like to see the impact of this type of the seismic sources on noise correlation, which is one of the most common technique in many applications in seismology. And also we would like to see the how seasonal behavior of the microseismic sources actually can map onto the noise correlation wave fields. And at the end, we would like to investigate actually another new techniques for characterizations of the microseismic sources in order to better understanding this type of the sources. So first, I have a short overview about the microseism. Actually, regardless the earthquake, the earth continuously vibrate, even we can feel it. Actually, that's caused by human-made and natural phenomena, which is ambient seismic noise, and microseismic sources, which is ocean-generated seismic waves, actually dominate the ambient seismic noise record, and also they continuously recorded and consistently shape the seismic background noise below 1 Hertz. Generally speaking, we have two main types of the microseismic sources. The first one is related to primary microseism that generate by the coupling of the oceanic swells onto the actually seafloor when the oceanic waves approach the shallow water. Also, they have the same wave period with the oceanic wave responsible for their generation, and there is a specific depth for the generations of the primary microseism. In the other hand, we have the secondary microseism, the most energetic type of the microseism, that generated by the two actually train of oceanic wave traveling in the opposite side. They generate the vertical pressure, can travel down and to the ocean bottom and generate as elastic waves. They have the half of the period of the oceanic wave responsible for their generations, and it's independent for the depth. They can generate in different depths. Actually, this is a quite revolution with this type of the seismic source in seismology. For example, we can investigate some important issues like climate changes or, for example, ocean monitoring like sea state modeling, tracking storms and sea ice coverage with this type of seismic source. For example, in this study, they try to characterize the secondary and primary microseisms due to some varying in the ice coverage in Atlantic. And also, on the other hand, there are a massive and many applications in monitoring and imaging in the actual seismology with this type of source. Also for for example, here in this study, they investigate the velocity changes few days before and after the major earthquake. So for actually do this type of the imaging efforts, we need to extract the signal from ambient seismic noise, which is the seismic interferometry method that I explained here. This method actually enables us to replace the source with receivers. So it means that we don't need to actually occurrence the earthquake anymore. Just in any locations, we can just, with the correlation observation between the seismic records at the same time between two stations, we can retrieve the information about the wave propagation in the media. However, we need a very important assumption when we want to use this method, that is uniform and isotropic distributions of the sources around the station pairs. In this ideal case, we have the very symmetric correlations that exactly or near close to the exact green function, and they can or retrieve the accurate information about the wave propagations between the station pairs in the positive and negative elapsed time side. However, in the real case scenario, we observe really asymmetric in amplitude and frequency content, which shows the violence of this actually assumption in the real scenario. So in addition to the direct arrivals, we have the later part of the coda, later part of the correlations, which is the coda, and they fully consist of the scatter wave field, which they travel point by point of the Earth. And also they use in the many applications for example, material properties or crustal behavior over the time, or for example, small velocity change detections. And for example, in this study that I mentioned before, they consider the coda is stable, and independent from the noise source distribution, which is ideal for the monitoring applications. However, we know that actually the microsized sources changes over the time. So we want to see that how the changes of the microsized sources can impact on the correlation wave field, specifically coda. So this is what I want to investigate in the first part of my PhD project. So I would like to just brief three main goals or questions we would like to address in this research. The first one, we would like to see that how actually are, for example, coda waves in ambient noise truly scatter, or some persistent and repetitions of the sources can impact on the microsize, on the correlation wave field or not, specifically coda. And as we know, for example, here the distributions of the noise microsized sources changes over the southern and northern hemisphere, and how these seasonality variations can impact or challenge the stability of the coda of the coda of the correlations. So in the third question, we just focus on the microsize, and we would like to see, for better understanding of the microsize, can we track them without relying to the dense network? For example, here we would like to see seismic array-derived rotation can get the similar insight for the microsize characterizations or not. First, let me show how we address the first two questions. The method we would like to use for the first two questions is the correlation wave fields. As I said, we need just the different stations. For the tracking the sources, we use the seismic array beamformings. That means we need also the array. And also for the first question, we would like to see how this type of the sources impact on the different type of the correlations. And also we would like to address this question in the primary microsize frequency band. And also in the second question, as I said, we would like to see how does coda follow the seasonal variation. Just with using the temporal resolutions across the season, we would like to answer this question in the secondary microsize frequency band. So for the correlations, as I said, for example, here I showed the different correlation we calculated, and we concentrate on the coda. For the this calculation, we define the dataset strategy, like here, one seismic array, Riefenbeck array in Germany, including 13 broadband stations, and we consider 6 single station as a master station in the different back azimuth regarding the Riefenbeck array. So for the reference correlation calculation, we consider each master station specifically, and also we try to compute the correlations between each master station and each seismic station inside the Riefenbeck array. So we have the 13 reference correlation per each master stations. So for example, here I show the reference correlations for the different master station and just one station in Riefenbeck array. As you can see, we have the different direct arrival time based on the different interstation distance, and we retrieve these 2 hours correlations by the just vertical recorded components, and also for the pre-processing and calculation, we follow just the outlier by Benson et al. 2007. And as I said, we also investigate the first question in the primary frequency band and second question in the secondary frequency band. So as I said, we would like to track by the seismic array beamforming. I just explain a brief about this method. This method enables us to extract the coherent wave fields from the non-coherent wave fields when wave propagate across the array. So on the other hand, we need the plane wave approximation that works best when the source located in the far field. And also we can parameterize the potential actually wave field propagate across the array by the grid search of the back azimuth and slowness, this apparent velocity. So we can find the locations of the sources by the, for example, best shift in the time domain, which is the delay and sum method, or by phase shifting in the frequency domain. And the higher beam power value actually shows the locations of the sources responsible for the recorded signals. It's very convenient that many studies use this method just for the original recorded data between the stations. Here, for the first time, we apply this method on the pre-computed correlations and to see what results can be achieved by these combinations. So, for example, in the first question, we would like to see how these combinations works, and we focus on the primary frequency band. I show here the first overview about the what we can achieve by these combinations. So here there is a distributions of the maximum beam power for the different back azimuth and slowness. And for the better understanding, I plot one of the reference station that we use for the beamforming method, just for example, for the BRMO master stations. As we can see, there are 3 different back azimuth here, 2 different, which is colored here, is related to 10 degree and 190 degree. That is related actually to direct arrival time. And when we can see to the, we take a look into the geometry of the master stations and BRMO here and center of the Greffenbeck array, this direction can be related actually to the wave actually propagate from the master station and towards to master station in the positive and negative elapsed time side. However, when we see to the actually later part of the correlation or coda, we see a very dominant and different directions from the coda. This is exactly related to the north and northwest of the Greffenbeck array, and also can be related to the macrosized wave field. However, for better actually estimation or accurate result, we first try to apply time windowing function with 10 minutes length throughout the correlations first, and we label based on the, for example, wave type, direct arrival, or early coda until the 1 hour end coda. And then we apply the beamforming method on each of these 10 minutes individually. And rather than this demonstration, the maximum actually beam power value, we try to actually plot all the average beam power we retrieve during the grid search of the slowness and back azimuth. So here, the radius axis shows the slowness, and also we see the same directions from the sources when we apply the beamforming, just specifically on the direct arrival, and this is what exactly we expect during the seismic interferometry. So, however, when we just apply for the different actually part of the correlation until the end of the coda, there is the same pattern in the same directions in the north and northwest of the Greffenbeck array. Just by investigations of the different master station in different back azimuth, we observe the same pattern for the coda. For example, here I show one of the master station, OJC in Poland. Again, the direct arrival is sensitive to the geometry of the master stations and receiver. However, coda is insensitive to this geometry. We would like also to see how Greffenbeck array itself see this macrosized wave field. So we apply this beamforming like conventional way on the original recorded inside the Greffenbeck array, and we see actually I just labeled like raw data beamforming, and we see again the similar directions comes from the north and northwest of the Greffenbeck array. That is related to the macrosized sources that distributed in the north and northeast end of the Atlantic. So for the key message of the question 1 is somehow we can challenge this assumption about the coda that is commonly assumed fully scattered. And also we see that these persistent microsized sources imprints until the end of the coda. And this can bias in some coda-based measurements. So in the last part or question 2, we would like to see if we assume this generates from the microsize, we should observe the seasonal variation as well. So we investigate this part in the secondary microsize and the frequency band. And I just bring the short overview about what we know so far about the seasonal variation in this method, in this region. Generally, seasonal variations of the microsize closely follows the oceanic storm activities. For example, during the local northern hemisphere, when we have the many oceanic storms in the local winter in this region, many studies detected actually southern tip of the Greenland and also Norwegian coast and western British Isles as most prominent sources for the microsize generation. Also, during the winter, when oceanic storm activities migrate to the southern hemisphere, we observe many source direction from the southern hemisphere. Also, some studies detect the P waves from the secondary macrosize teleseismic P waves that are related with the strong oceanic sources that responsible during the summer in the southern hemisphere. And they have the actually very fast velocity. So first, I would like to check first the seasonal variation inside the Riefenbeck array, and then we can compare with this results with the correlations function. So we apply the beamforming on the original recorded data in the monthly resolutions, for the 30 stations of the Riefenbeck array. As we can see, during the winter months, most of the directions comes from the west and also the north. That is related to the actually major sources that I addressed in the previous slides. However, when we just take a look to the months related to the summer, we see the dominancy of the P wave specifically in May until the August. That is related to the teleseismic P waves that I mentioned before. They have the slowness range less than the 0.1, and also we can explain the strong the dominancy of the P wave by strong attenuations of the surface waves to large propagation distance. So when we just take a look actually to the macrosize analysis, we try to retrieve the reference correlations for the 2 6 months related to the winter, and then we apply the beamforming on the pre-computed correlation. As we can see, regardless to the complex pattern that in comparison the primary microsize, we still see the directions from the west and also north that is related to the actually surface waves slowness. When we just take a look to the 2 6 months related to the summer, specifically CODA observed the P wave actually contributions with a very fast velocity when they arrive vertically to the Riefenbeck array. In this plot, we can see actually where is the directions of the P wave and to foresee that where the source comes from. So for this observation, I just provide another representations. I just switch to the maximum B power again and plot the average wave height in the actually global scale during the winter and during the summer. As you can see again, we see that the seasonal variation follow closely actually the storm activities, and this maximum average wave height responsible for the P wave generation. And when we see to the distributions of the maximum beam power, we see that they are weighted by the slowness. we see that the most distribution concentrate to the south, and also the slowness related to the body waves or P waves. When we see during the winter, again, the maximum distributions of the beam power is directions of the north and northwest, and it's related to the surface phase slowness. So here, for the second question, the key message we can actually understand is that, yes, CODA can actually follow closely the seasonal variations, and this can be actually impact on the stability of the CODA when we have the migrations of the sources during the winter and summer. And also we see the contributions of the different wave type to the CODA as well. So this lack of the consistency can be a problem for some monitoring applications. So in the third question, I just rephrase a little bit here for giving you the more information. We would like to characterize actually the macro-sized wave fields with another new technique, which is called the array drive rotation, as they mostly contain the surface waves. We would like actually to see that how we can characterize the macro-sized wave field into the Love and Riley wave by this method. So here, the strategy we have, first of all, we would like to actually characterize the Love and Riley wave using the array drive rotations. And the requirement is this small seismic array or small size seismic array, which I explain in detail in the next steps. And also we would like to characterize the same parameters using the three-component beamforming, which is the same strategy with the single component that I explained before, but the extent for the three-component and allows us to investigate the polarizations or wave type as well. So what we need is a conventional seismic array, or let's say a large size seismic array. And in the next step, we would like actually compare these results with each other in the secondary and primary frequency band. What we need is that we have to use these two seismic stations close to each other. And as I said, we would like to address this question in the primary and secondary macro size frequency band. So let's I have a short overview about the array drive rotation. Actually, there are some advantages when we want to use this method. The first is this, thanks to requirement for the small size array, there is a very easier and also convenient way for the design and installations of the seismic sensor by this method. Also, we can retrieve the extra information about the displacement wave fields, not only about the translational motion, which is related to the change of the positions of the material when wave fields propagate through them, but also about the rotational motions. So in the other part, this method can, similar to the beamforming, localize or detect the directions of the waves comes from to the signals by comparing the rotational measurement and accelerational measurement in the three different back azimuth. Also, there is the possibility and open the new door for using these rotational investigations for the macro size with a single rotation sensor as well. That is really important. So first of all, I would like to show the result for the array drive rotations. Since there are quite few number of the small size seismic array in the global scale, we have to change our location to the California. We choose the Pinon flat array with 13 stations and quite a small aperture size, convenient for the macro size studies. And here we use the 4 years time span for investigations of the macro size. So for the array for the three-component beamforming, as I said, we want to choose the closed seismic array to the non-flat array. So we use the 21 combinations of the seismic stations inside the 2 seismic array in California. And also we use the 4-year time span, same time resolution for investigations. So we would like to compare the results between 2 methods as well in 2 frequency bands. First of all, I explain a little bit about the results for the array drive rotation. Actually, these are the distributions of the correlation coefficients in the grid search of the back azimuth when we just investigate the similarity between the rotational and accelerational measurements. So as you can see, during the summer, rather than the number of the back azimuth range, I use the direction for the better understanding. As we can see, during the winter, there are repeated sources that repeated each summer from the southwest directions. When we see the results for the primary Rayleigh waves in the 3-component beamforming, we see the same directions for the 3-component beamforming as well. However, when we want to actually check or investigate the directions from the source during the winter, there are 2 different directions responsible for generations of the actually microsized in winter. That is related to the north, east, and northwest, and it's can be observed in the 3-component beamforming. That can related to the actually North Pacific and Atlantic Ocean when we have the many storm activities during the winter in Northern Hemisphere. So when we see the primary love wave result, regardless to the actually a little dispersive distributions of the correlation coefficient in grid search of the back azimuth, we see the same directions for the summer and winter, but a little bit difference during the summer that can be more visible or can be better detected in the some 3-component beamforming results. So, however, when we just check the seasonality for the secondary love waves, we see very stable seasonality changes during the summer and winter, and actually mostly the source coming from the southwest, and this is detected or observed in many also other studies when they located microsites in this region. And also we can observe in the 3-component beamforming results as well during the summer and winter. So, however, about the love wave, we observed a similar more or less pattern with the actually Rayleigh wave in array drive rotation, a little more actually broader back azimuth range retrieve for the love wave, but we see and we can observe the more variant back azimuth that's detected by the 3-component beamforming and difficult to detect in the array drive rotation. So in conclusions for the question 3, yes, a small aperture size method array drive rotation can actually effectively track macro-sized sources, and they can use for the characterizing the love and Rayleigh waves, and there is in the most of the cases agreement between these results with the 3-component results. Specifically, we saw the maximum similarity for the Rayleigh waves. And here I would like to conclude my presentations. For the question 1, we somehow challenged the assumption about the actually fully scattered wave fields of the coda, and we show that in some cases coda may not fully scatter. And also we observe the imprint and wear correlations of some persistent sources here, the microsized sources, in the different part of the coda until the end. And also we observe the seasonal variation in the actually coda investigations, and coda may closely follows the seasonal behaviors of the microsize. And actually about the using the new techniques like array drive rotation, they can effectively detect the low frequency microsize, and there are agreements between them and three-component beamforming. However, still three-component beamforming can have a finer resolutions for the different directions when sources act in the same time. So as research, there are many open questions that are very important to explore. I would like just here to mention to a few of them about the coda of the correlations. The first, still we know that the coda contains the scatter wave fields, but how we can model the coda composition and what is the ratio of the contributions of the persistent sources like here, Microseism and scatter wave fields in the coda when we want to use them. And also when we observe this a high degree of the seasonal variations, what should be the actually error when we use velocity changes or velocity changes monitoring, and the method that can be correct or remove this effect. It's very important. And also, we know that the coda correlation, the coda of the correlation C3 method used for actually improve the scattering behavior of the coda of the correlations. However, by these observations, C3 can suppress this bias or can amplify. This is also a key question we can address. So I end now my presentation and thank you for attention.